Welcome to CMAC Explained. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today, we're diving into the world of cryptography to understand a very important algorithm called CMAC, which stands for Cipher-based Message Authentication Code. You might be wondering what that long name means. In simple terms, CMAC is a way to ensure that a message you receive is authentic and hasn't been tampered with. It acts like a digital seal or signature that verifies both the sender's identity and the message's integrity. Throughout this presentation, we will explore what CMAC is, why it is needed, and how it works under the hood. We will see that it uses a familiar building block, a block cipher like AES, to generate this special tag, or MAC. This process provides a high level of security and is a fundamental component in many secure communication protocols that we use every day, such as TLS and IPsec. What is a MAC? Before we can fully appreciate CMAC, we need to understand the core concept it is built upon. A Message Authentication Code, or MAC. So, what is a MAC? A MAC is a short piece of information used to authenticate a message. Think of it as a cryptographic checksum. The sender takes the message and a secret key, which is known only to the sender and the intended recipient, and feeds them into a MAC algorithm. The output is a fixed-size string called the MAC tag. This tag is then attached to the message and sent. When the recipient gets the message, they perform the exact same calculation using the message they received and their copy of the secret key. If the tag they generate matches the one that came with the message, they can be confident about two things. First, the message came from the sender who holds the secret key, which confirms authenticity, and second, the message was not altered in transit, which confirms integrity. If the tags don't match, it means something is wrong. Either the message was tampered with, or it didn't come from the expected sender. How CMAC works. A high-level view. Now let's look at CMAC specifically. The C in CMAC stands for cipher-based, which tells us that it uses a symmetric block cipher, like the Advanced Encryption Standard, AES, as its core engine. This is different from other MACs like HMAC, which use hash functions. Here is the process at a high level. First, the message is broken down into fixed-size blocks that match the block size of the cipher. For instance, 128 bits for AES. These blocks are then processed one by one in a sequential manner, similar to a mode of operation called cipher block chaining, or CBC. The result of encrypting one block is XOR'd with the next block before it gets encrypted. This chaining process ensures that any change in one block affects all subsequent blocks, making tampering easily detectable. Finally, after the last block is processed, a special final step is performed to produce the CMAC tag. This entire process depends on a single secret key that both the sender and receiver share. The secret sauce. Subkey generation. A crucial and unique part of the CMAC algorithm is the generation of two special subkeys, known as K1 and K2. These subkeys are not provided by the user. Instead, they are derived directly from the main secret key, K, at the beginning of the process. This subkey generation is what sets CMAC apart and fixes security flaws found in earlier CBC-MAC algorithms. Here's how it works. First, the block cipher, like AES, encrypts a block of all zeros using the main secret key K. The result is a block of seemingly random bytes. This block is then put through a special mathematical operation, which involves checking its most significant bit and performing a conditional left shift and an XOR operation with a predefined constant. This process creates the first subkey, K1. Then, a similar operation is performed on K1 to generate the second subkey, K2. These two subkeys are then used only in the final step of the CMAC calculation, depending on whether the original message was a perfect multiple of the block size or not. This clever design prevents certain types of attacks and ensures CMAC's security for messages of varying lengths. The CMAC process step by step. Let's walk through the full CMAC process step by step to see how all the pieces fit together. First, as we discussed, the two subkeys, K1 and K2, are generated from the main secret key, K. Next, the message is divided into blocks, M1, M2, and so on, up to the last block, Mn. The process then begins, operating like CBC-MAC. The first block, M1, is encrypted with the key K. The output of this encryption is then XO-read with the second block, M2, and that result is encrypted. This chain reaction continues for all the blocks until we reach the final one. Here's where the special handling comes in. If the last block, Mn, is a full block, it is XO-read with subkey K1 before the final encryption. However, if the last block is incomplete, it must be padded to a full block, and then it is XO-read with subkey K2 before the final encryption. The output of this final encryption step is the CMAC tag. This final step using K1 or K2 is critical for the security of the algorithm. The importance of padding. In the world of block ciphers, data must be processed in fixed-size chunks or blocks. But what happens when the message does not perfectly divide into these blocks? This is where padding comes in. Padding is the process of adding extra bits to the last block of a message to make it a full block. In CMAC, the padding scheme is very specific and crucial for its security. If the last block is a full block, no padding is needed, and we use the subkey K1 in the final step. However, if the last block is even one bit short, it needs to be padded. The CMAC standard specifies that you append a 1 bit to the end of the message, followed by as many 0 bits as necessary to fill the block. For example, if the block size is 128 bits and the last block has only 100 bits, we would add a 1 and then 27 zeros to make it 128 bits. After this padding is applied, the padded block is then processed using the other subkey, K2. This clear distinction in handling full and partial blocks prevents ambiguities and attacks where an attacker could craft a message that, after processing, results in the same MAC tag as a different message. CMAC versus HMAC. CMAC is not the only popular MAC algorithm out there. Its main competitor is HMAC, which stands for Hash-based Message Authentication Code. While both serve the same purpose of providing integrity and authenticity, they are built differently. The primary difference is their core component. CMAC uses a block cipher like AES, while HMAC uses a cryptographic hash function like SHA-256. This fundamental difference leads to different performance characteristics and use cases. HMAC is often faster in software implementations and is extremely popular on the Internet, used in protocols like TLS and IPsec. On the other hand, CMAC is often preferred in environments where a block cipher is already being used for encryption, such as in embedded systems or certain government standards. This allows for a more compact implementation, as you don't need to include code for both a cipher and a hash function. In terms of security, both are considered highly secure when implemented correctly with standard components. The choice between them often comes down to the specific system's requirements and existing cryptographic libraries. Practical use cases of CMAC. So, where is CMAC actually used in the real world? Its applications are widespread, particularly in systems that require both efficiency and strong security guarantees. One of the most common areas is in secure communication protocols. For example, it is an approved algorithm for use in government applications as specified by NIST, the National Institute of Standards and Technology. CMAC is also widely used in authenticated encryption modes like AES-CCM, which is prevalent in wireless networking standards such as Wi-Fi 802.11 and Bluetooth Low Energy. In these resource-constrained environments, Reusing the AES engine for both encryption and authentication via CMAC is very efficient. Furthermore, you can find CMAC used in payment systems for authenticating transactions, in digital signatures, and for ensuring the integrity of stored files to detect any unauthorized modifications. Essentially, any application that needs to verify that data has not been altered and comes from a trusted source can benefit from using CMAC. Advantages of using CMAC. Why would a developer or a security architect choose CMAC? There are several key advantages. First and foremost is its strong security foundation. CMAC is provably secure, assuming the underlying block cipher is secure. It was specifically designed to overcome the security limitations of its predecessor, CBC-MAC, for variable length messages. Another major advantage is efficiency, especially in systems that are already using a block cipher for encryption. Since CMAC can reuse the same cryptographic engine, it saves code size and memory, which is a significant benefit for embedded systems, IoT devices, and smart cards. It is also standardized by organizations like NIST, which means it has been thoroughly vetted by cryptographers and is considered a reliable and interoperable choice for building secure systems. Finally, its performance is excellent, especially when implemented in hardware, making it suitable for high-speed networking applications where data integrity is paramount. Summary and conclusion. Let's quickly recap what we've learned about the CMAC protocol. We started by understanding that CMAC, or Cipher-based Message Authentication Code, provides two critical security services: data integrity, ensuring a message hasn't been altered, and data authenticity, verifying the message's origin. We saw that it's built upon a symmetric block cipher, like AES, and a shared secret key. The key to its security lies in its clever process, which involves breaking a message into blocks, chaining them together using encryption, and applying a special final step with one of two derived subkeys, K1 or K2. This process, including a well-defined padding scheme, makes CMAC secure for messages of any length. We also compared it to its hash-based counterpart, HMAC, and noted its advantages in environments where a block cipher is already in use. From securing wireless communications to financial transactions, CMAC is a powerful and efficient tool in the world of modern cryptography. Thank you for your attendance. Please consider subscribing to the channel.